Today's webinar will be presented by Patrik Andersson. Patrik is a product specialist at Xray Tube, and he will provide you with some in-depth knowledge of this important topic. Let's kick it off, Patrik.
This is the contents of today's webinar. We will start with an introduction to how the X-ray machine works and common hardware failures that can occur because of wear and tear. Then we will talk about why testing is important to ensure patient and staff safety. And the punchline for this webinar is that proper testing can be used for predictive maintenance to increase uptime and lifetime of the X-ray machine together with reduced dose to staff and patients. But why do we need to do QA measurements? Quality assurance tests are first done to establish measurement references, and thereafter they serve to uncover possible malfunctions or wear and tear problems in the X-ray machines over time. As we will see, there are several problems that can occur in the X-ray machine which regular quality assurance testing can detect at an early stage. Malfunctioning of an X-ray machine is not only expensive due to new parts and downtime, it can also lead to increased dose to both patient and staff. And to avoid unnecessary dose should always be top priority if one is working in accordance with the ALARA principle. Most of you are probably aware of this concept, but we must always have this in back of our mind when discussing today's topic. In accordance with ALARA, one must always make everything one can to keep the dose as low as reasonable achievable. There is no known level of safe radiation, and the good of an exposure must always be greater than the potential risk of the exposure. Okay, time to get a bit more specific and talk about how change in output of the X-ray machine will affect not only the uptime of the machine, but also the dose to patients and staff. Before we go into details on QA testing, let's make a recapitulation and describe the Xray tube. X-rays is made inside of a vacuum container, usually made of glass or metal. The reason why it is vacuum inside is that electrons cannot accelerate in air. The Xray tube has two crucial parts. We have the anode and the cathode. And the cathode has one or two metal wires called filaments. Then they are usually made of tungsten to withstand heat. When the filament is heated by electrical current, the electrons are released as a cloud around the filament. The difference in electric charge between the anode and the cathode makes these electrons accelerate towards the anode plate. When the electron hits the anode, they stop very suddenly and transfer the energy into X-ray photons, which are emitted through an exit opening of the tube. For radiography, the anode is often also made of tungsten to withstand high temperature caused by the electrons that hits it. The angle of the anode and the rotation makes the heat disperse over a larger area. And this angle of the anode will also impact the quality and the energy of the X-ray produced, because it affects how deep the electrons will penetrate in the anode material, and also the size of the focal spot where the photon hits the anode. An X-ray machine needs to have a beam restricting device in order to minimize the X-ray dose and improve image quality. The beam restricting device does that by limiting the X-ray field to the right size for the diagnostic procedure and by reducing scattered radiation. The most commonly used device is called a collimator. The primary collimator is located at the opening of the X-ray tube, and the secondary collimator is placed inside a collimator house and has two sets of LED shutters that can be adjusted to make the X-ray field size smaller or bigger in a rectangular or square shape. There is also a light bulb that illuminates the X-ray field to show its size and center. The light bulb must be mounted so the X-ray field and the light field match each other. And this is how a collimator housing may look in real life. So this is mounted at the opening or the exit of the X-ray tube. There are several problems that are likely to occur with wear and tear in the X-ray machine. Every time X-ray is produced, the filament gets heated due to the current flowing inside of it. This heat may lead to evaporation, meaning atoms may disappear from the filament. The amount is usually extremely small, but with time it will influence the filament thickness. And if the thickness changes over time, the current flowing inside changes since the resistance has changed. Modern machine will autocorrect for this by changing the voltage over the cathode, but with time the filament will eventually break. Another phenomena that will occur with time is tube blackening. As atoms get vaporized in the filament, so are also the anode atoms. These atoms will be deposited on the inside of the X-ray tube, causing the glass to blacken over time. This will affect the quality of the X-ray beam since radiation will pass more matter and get shielded compared to a clean glass. The anode will also suffer from wear and tear, not only caused by vaporization. With use, it may become rougher, affecting the radiation quality. The photograph here shows a well-used anode. The repeated heating and cooling has roughened its surface. It also has been exposed when not rotating, which has resulted in a locally melted tungsten spot. The intense heating of this small area has in addition caused an expansion, which has resulted in a small crack. If the anode then starts to rotate again, this crack may propagate, leading to a complete disc fracture. The roughening of the focal track will cause a drop in the output and change the radiation output spectrum. As the filament shape changes with time, together with anode wear and tear, the focal spot will also be affected. In general, a small focal spot is used when spatial resolution is important. A large focal spot will induce more photons per time, meaning a shorter exposure time is possible. Also, a larger focal spot is less sensitive to heat since it's spread over a larger area. Another thing to consider is the collimator light and X-ray field alignment. A reason for it to be out of alignment would be if the machine has received a blow or if handled roughly, which has caused the lamp inside of it to shift. The light field from the collimator housing represents the area that is to be irradiated by the X-ray beam. If the X-ray field is not aligned with the light field, the operator may take a picture not fully containing the whole area, meaning another picture must be taken, which takes time and increased dose. There is also a chance that the operator takes a picture that is too big, leading to unnecessary dose to the patients. Tube leakage is also something to think about. The tube must be completely closed and there should be no radiation coming out of it except through the exit hole. There might be design flaws making it not completely closed. They can also be damaged if it has received a blow or other type of rough handling. And just to show, here I have this heavy piece, a tube where the tube housing where the X-ray tube is mounted inside of it, and the X-ray are emitted through the exit hole at the bottom. This was the end of the first part of this webinar. We have mainly focused on the X-ray tube hardware. We will now focus more on the softer and maybe more abstract parts, namely safety. Okay, let's start with the concept QA testing. We have earlier stated that the output of the machine can tell us something about the aging of it. Consistent output of the machine is important for the image quality and correct diagnosis while keeping the dose at a minimum, but also to uncover possible malfunctions or wear and tear problems in the Xray machine over time. But why do we need to do QA measurements? This is mainly driven by regulation to ensure patient and staff safety, but there are also some economical incentives. Malfunctioning of an Xray machine is not only expensive due to new parts and downtime. Malfunctioning can also lead to increased dose to both patients and staff. And avoid unnecessary dose should always be top priority if one is working in accordance with ALARA. Making sure that the Xray machine's output is consistent over time is of great importance if one would like to minimize patient dose. One should always strive towards getting as good image quality as possible without giving the patient unnecessary dose. The advantage of the exposure must always be greater than the potential risk. Before we continue further with patient safety, I will linger a few more minutes on the economical point of view. If one has a proper knowledge about the aging of the Xray machine, one can more easily plan for maintenance, heavily increase its uptime. If the machine unexpectedly breaks, it may take a long time for it to be repaired, and it will heavily affect the number of patients treated, and in some cases, also the income of the medical facility. Aging machine may also affect image quality. The worst case scenario is that the wrong diagnosis is made due to lack of information, but multiple images taken due to low quality also lead to higher dose to the patient and longer screening sessions. Longer screening sessions also mean fewer patients per day. Okay, we will now focus more on the safety bit of the QA testing. All these hardware problems we have discussed also affect the output of the machine, and it's crucial that the Xray machine's operator knows the status of the machine. By knowing the status, the operator can give the correct settings to the machines, meaning a high quality picture can be taken with the dose to the patient is at its minimum, all in accordance with ALARA. If it for some reason does not give the same output as before, it may affect patient and staff safety. So let's walk through some of the parameters measured during QA and try to understand how these will affect the machine output. Let us start with the parameter kV, a parameter affecting the image quality. The kilovoltage, or the kV, is the tube potential and the energy of the electrons that are accelerated towards the anode target. For use in medical imaging, the kV usually ranges between 20 to 150 kV, depending on the Xray modality and the type of diagnostic procedure. A high kV on the Xray machine would produce radiation with high frequency, high energy, short wavelength, and strong penetration. Radiation with these qualities is referred to as hard X-rays. A low kV settings on the Xray machine will produce radiation with low frequency, low energy, long wavelength, and less penetration. Radiation with these qualities is referred to as soft X-rays. A way to measure kV is to measure the energy of the radiation. The photon spectrum contains of energies between 0 and the set kV. If the machine is set to 120 kV, at least some photons should have that energy. And by looking at the highest energy photons in the spectrum, we can acquire kV, and we call it kVp, which stands for kV peak. If there is a change in the kV on the machine over time, it will affect the quality of the image taken. Most likely, there is something wrong with a controller inside the generator. There may also be wear out circuits, making it hard for the machine to ramp up the kV fast enough. A third option may be that there is a flaw in the power grid. Milliamp MA is the electrical current flowing through the filament. Since the MA controls the number of electrons hitting the anode per second, it is directly related to the quantity of X-rays produced. Milliamp second mass is the MA multiplied by the exposure time in seconds. The mass value determines the total number of photons delivered during an X-ray exposure. There are mainly two ways of measuring mass. One can measure it invasively by hooking a sensor to the internal circuit in the X-ray machine. By doing this, one will measure a current corresponding to the same current going through the filament. The second way is non-invasively. The one is measuring the electric field around the high voltage cable feeding the generator. There is also a third way, and it is to measure dose from the machine output. Dose is directly related to mass, but one can still not make too big conclusions since there are more parameters in place affecting the dose. But measuring dose can be a first and easy step to get an indication of a changed mass. If mass is changing over time, it will change the quality of the X-ray image taken. Most likely there is something wrong with the internal circuits in the X-ray machine. Thinning of filament will change mass, but it is usually controlled by the X-ray machine itself. Another fault can be a flaw in the power grid. Half value layer, or HVL, is a more abstract parameter explaining the machine output. One way to control the photon spectrum is by using filters. By adding filters, one will change the relationship between high and low energy photons. The optimal relationship between these two depends on the modality and which part of the patient that is being imaged. One parameter used to explain this photon relationship is HVL, the half value layer. It is defined by how much aluminum one needs to decrease the dose to 50%. More shielding will affect the half value layer HVL. A low HVL means a bigger share of low energy photons compared to a high HVL. And a change in HVL means a change in beam quality, which affects the X-ray image quality. There are mainly two ways of measuring HVL. The manual way is to first measure dose, then add filters until the measured dose is 50% of the original dose. These type of measurements are extremely hard to do and uncertainty is high. After the entrance of solid-state sensors instead of ion chambers, one has been able to get enough information out of the exposure so HVL can be calculated directly from a single exposure. All previously discussed hardware defects will affect HVL. Filament and anode vaporization will add to the filtration. Roughening of the anode surface may also change HVL. Dose is a combination of kV and MA together with HVL, and it contains the information to the image receiver. If you have a high MA and therefore a lot of photons, you will get a high dose. If you have a high kV, you will also get a high dose. If the information to the image receiver is perfect, a high quality image can be reconstructed by the computer while the patient has received minimum dose. If the information is bad, it will lead to poor image quality. This may lead to faulty diagnosis or that more images must be taken. Since dose is the product of all other parameters, any X-ray machine hardware defects will most likely affect the dose. By combining changes in dose, kV, mass, and HVL, one can make certain conclusions of the machine status. Other types of measurements not fully relying on the beam quality is the light and X-ray field alignment. If the machine has received a blow or such, the light bulb, which generates the light field, may be out of place. The operator should always try to make as a small picture as possible to increase image quality and minimize patient dose. If the field is misaligned, there is a chance that the operator takes a too small image, leaving out valuable information. If information is left out, a wrong diagnosis may be made or more pictures may need to be taken, both affecting patient safety. If the picture taken is too large, patient has received unnecessary dose. Focal spot measurement can also be made to see if it matches the size given by the manufacturer. Making sure that the X-ray machine output is well known and consistent is of great importance if one would like to make good quality image together with minimum patient dose. One should always strive towards getting as good image quality as possible without giving patient unnecessary dose, all in accordance with ALARA. Unnecessary dose is given if there is too much low energy photons present that gets absorbed in the body, or the image taken is not including the whole interesting area, or the image taken is including more than the interested area, or if the image quality is poor and more image must be taken. We will also talk about minimizing dose to staff. In most applications, staff is not close to the source when an image is taken. They usually leave the room or go behind shielding. The patient always gets the highest dose during a procedure, but staff, on the other hand, are exposed to small amounts of radiation every day, and the accumulated dose over years can be quite high. It is therefore of utmost importance to control the environment also from a staff perspective. When an exposure happens, it will scatter radiation all over the room. If the operator is behind a shield, it is still important to measure the efficiency of the shield. Also, the geometry of the room can give local hotspots of scattered radiation. If there's a tube leakage, a high energy unfiltered beam is propagating in the room, creating even more scatter, maybe behind the shield. If the staff is outside the room, or if there is a busy hallway outside the room, it is important that the wall is well shielded. Otherwise, staff and other patients may receive unnecessary dose. A usual way to shield a wall is by having lead plates inside of it. If the lead is damaged in any way, or if the plates have been poorly assembled in the wall, there might be radiation leaking out. One should therefore always do wall leakage measurements before commissioning and startup of the X-ray room. A special type of X-ray modality where staff is exposed to high doses is fluoroscopy. Fluoroscopy is a technique mainly used during surgeries, for example, during heart surgeries. The surgeon may insert instrument in a major blood vessel, guiding the instrument up to the heart via the blood vessel. But to be able to do this, the surgeon must know where the instrument is. By having a pulsed exposure with a high frequency, one can follow what's happening inside the body in real time. Since the exposure time is seconds at a time, and maybe 30 minutes of total exposure time during the surgery, the energy of the photons must be much lower compared to regular radiography. Otherwise, the patient and the staff in the surgical room will get insane amount of dose. Even though the energy is low, the procedure time is long. If the machine gives too much dose than required, the increased accumulated dose to the staff over years may be significantly higher. If there's something wrong and the machine gives a lot of more dose than it should, it is also a danger for the patient. Not does it only increase long-term illness, it can also give short-time damages such as burns or dead tissue. Of course, tube and wall leakage in these types of rooms are also important, especially since the exposure times is so long compared to other modalities. We have so far talked about the Xray tube and different hardware problems. We have also talked about why QA testing is important when it comes to uptime of the machine, together with patient and staff safety. We will start to slightly switch focus to the actual testing and the products involved in testing. A few words about the tests themselves. The ones we display now are only a few tests one can do. Exactly which tests are required differs from country to country. Even if countries have the same tests, they might have different procedures and acceptance criteria. It is therefore of utmost importance that one is aware of the local regulations. Except testing the regular parameters such as dose, kVp, and mass, one can also test the consistency and reproducibility of the machine. One is then doing several identical exposures and the output must be the same. Luminance test is nothing we really touched upon yet. This is not related to the machine. Luminance test is made on screens or monitors showing the X-ray image. If it, for example, is too dark in certain areas, the wrong interpretation of the image is at risk. And one does not want the same image to look different on different monitors. Sensors used for medical imaging QA measurements have historically been different types of ion chambers. Using ion chambers made the QA procedure more complicated since they can only measure dose and dose rate easily. You had to do several different types of time-consuming measurements to receive kVp, HVL, and so on. Not only is it time-consuming, but several measurement setups also give higher risk for errors. On top of that, ion chamber may also be highly sensitive to variation in temperatures and pressure. Since the entry of the solid-state detectors, measurements have been more time efficient and accurate. You receive all interesting parameters in just one irradiation. You also do not need to worry that much about scatter radiation. Especially when measured with an ion chamber, scatter radiation can make a big unwanted contribution, up to 30% at a dose. Even though solid-state detectors together with their integrated computational power are the best options for most QA measurements, there can be big differences between different detectors. The solid-state detector has a certain energy dependence, meaning that it can only interact with certain energies of the incoming photons. By putting shielding material with different thickness over different diodes, one can create a system of diodes that interact with the full energy spectrum of the diagnostic X-rays. The first diode has a small amount of shielding, or none maybe, and it can only interact with low energy radiation. The second one has slightly more shielding, and they can therefore interact with radiation of higher energy and so forth. By having many diodes, you will also have many channels with information. And by combining information from many channels, one can calculate a lot more from the radiation. For example, the amount of low energy photons compared to high energy photons. RaySafe has developed a truly unique QA system that can handle most of the QA measurements required. The main technology in our system is based on solid-state detectors, but does also contain a pencil-shaped ion chamber used for CTDI. Radiography and fluoroscopy are two often used modalities within diagnostic imaging. The X2RF sensor gives you all wanted parameters with high precision for both modalities. It also has a small radiographic footprint, especially useful in fluoroscopy, where the automatic brightness control is used. Mammography is maybe the trickiest modality to measure on. The breast tissue is not that dense, meaning one must use low energy photons to get good images. Here one can see a typical mammography machine with different anode and filter combination. If we look at a generic photon spectrum, here in the top left corner, one can see some peaks and sudden drops in the spectrum. And these peaks and drops are material characteristics. By combining different materials, one can use these peaks and drops to construct an optimal spectrum for different types of breasts. Not only does mammography machine have a much more complex photon spectrums compared to regular radiography, the small geometry and big variations in anode angles and materials between each machines makes it even harder to do proper measurements. The X2 mammography sensor can handle all kinds of difficulties occurring when measuring on mammography. What makes our product stand out is the ease of use. Even though mammography photospectrums are complex and differ between machines, RaySafe has been able to develop a mammography sensor with minimal number of settings. One can measure dose, HVL on all clinical machines on the market without any settings at all. If you would like to measure kVp, apply a single setting and you are able to measure kVp on all diagnostic mammography machines on the market. The MAM sensor has an increased window for dose, meaning one can use it for wide tomosynthesis sweeps as well. And the simplicity is a unique feature for our X2 system. Competitors' devices require many more settings for dose and kVp before a measurement can be made. And more settings makes it more complex with a higher risk of human errors. A computed tomography or CT machine uses a thin beam that rotates around the body. To be able to measure dose properly, the sensor must be able to pick up radiation from the whole 360-degree rotation. The X2 CT sensor is a pencil-shaped ion chamber with an electrometer built into a compact unit. Since it is an ion chamber, it will pick up the radiation for the full 360-degree rotation of the CT X-ray tube. It has a built-in pressure sensor and a thermometer. This gives us a signal that is automatically temperature corrected for the air temperature inside the ion chamber and not the room. All the sensors are connected to the X2 base unit via USB cables. All parameters are easy to see on the screen, and one can even look at the waveform and make waveform analysis directly in the base unit. The base unit also includes a mass sensor, meaning no additional external mass sensor is required. We have, of course, other products in the RaySafe portfolio that can help you conduct full-scale QA measurements. X2 light sensor is for checking the monitors, showing the X-ray image, making sure they have the right luminance. DXR is our ruler that can help you with the light X-ray field alignment. We also have different type of pinholes and slits for checking the focal spots on the X-ray machine. We also have products with focus on radiation protection. The X2 system has a survey meter, a perfect meter when it comes to measuring scatter or tube leakage from diagnostic imaging machines. But I would also like to promote the RaySafe 452 here on the screen. This is our newest product in the RaySafe family, and it's a versatile survey meter with a huge application range. Not only is it perfect for scatter and tube leakage measurements, but it also has a much wider energy range, making it an excellent option for higher energy photon applications such as radiation therapy or linear acceleration and so on. It can also be used as a contamination meter, which is of great help at radiotherapy clinics. Our real-time dosimetry system, i3, is also a great product when it comes to decreasing dose to staff during fluoroscopy. A dosimeter is placed on the staff in the operating room. By giving staff instant visual feedback on the received dose during the exposure, they can take immediate actions and change working procedure to lower their doses. Finally, we will conclude this webinar by just a few words about standards. QA testing is regulated by law to ensure patient and staff safety. Regulations differ depending on country and sometimes even region. It is therefore of utmost importance that medical physicians, radiation officers, or whoever is in charge of these questions at the hospital is well informed about regulations. If the regulations is not specifying a certain method on how to do a certain measurement, the same person must create his method, him or herself, and make certain that it is fulfilled.
Thank you so much, Patrick, for a fantastic presentation. There is more information available under the handout section here in GoToWebinar. Now it's time to engage you, our audience, in a Q&A session. We have already received some great questions, but we encourage you to send in more. First question up is, do the ray-safe dosimeters Xray and X2 measure kerma or absorbed dose?
Yeah, they are measuring in air kerma and not in absorbed dose.
Okay, great. Is there a minimum area that needs to be irradiated on the X2 RF sensor in order to correctly measure KV?
Yeah, let me see. I have, maybe it's easiest to show. I have the sensor here. As you can see on the sensor, it has a little slit here, and this is the opening window of the sensor, and the field should irradiate at least this area of the slit, preferably a little bit larger. So if you irradiate the circle around the slit, then you're all good to go.
I think actually this belongs to this question. Example, dental panoramic X-ray systems measuring KV. Image receptor, more difficult to position X2 in exposure area, wider exposure area of X2 sensor, more accurate KV measurement versus measurement collimator exit, easier to place X2 visual but wrong KV measurement. I don't really know.
No, I'm not really sure I understood that question, so maybe we can have a look at it later and I can give a better answer.
Yeah. Okay, so let's take the next one. You said that measured milliamp or mass is a corresponding current. It is not the actual current going through the filament?
Most often it is not. On more modern machine, there is a parallel circuit where you connect the mass cable. So the machine produces an equal current in this circuit as the one going to the filament. There are really no differences in doing measurements, but maybe one can argue that it's a little bit more safer with this parallel circuit when it comes to electrical safety.
The CT sensor can temperature correct itself depending on the temperature inside the ion chamber, not the room. When is the temperature inside the ion chamber and the room not the same?
It is true that most hospitals have good air conditioning and control of their environment. But let us assume that you are going to do a CTDI measurement using a CTDI phantom. These phantoms are huge and usually come in big suitcases and so on. So if you're traveling with this phantom, it is not too uncommon that it stays in the car for hours. And the temperature in the car can either get very warm or very cold, depending on where in the world you are. Then this phantom will get a different temperature than the ambient temperature in the hospital. And since they are so big and dense, it will take many, many hours for it to get the same temperature as the ambient in the hospital. So that's why it is better to measure the temperature inside the ion chamber itself, since it is placed inside the phantom and not outside of it.
Can you give an example of a measurement that differs between countries?
The first thing that comes into mind is dose measurements for mammography. In most places of the world, the dose sensor should be placed 6 centimeters from the chest wall and elevated 4 centimeters. But in the US, for example, the meter should be placed 4.5 centimeters from the chest wall and elevated 4 centimeters and elevated 4.5 centimeters in the US. Another thing that comes into mind is measuring on monitors using a light meter. In Germany, there can be requirements saying measurements should be made from a distance. In most other countries, the meter should have contact with the monitor itself.
In my country, I do not believe there are any specific regulations. What do I do?
That is a tough one. You need to read international standards and try to follow them as good as possible. As I said just earlier, if there aren't any regulations in place, you are responsible in creating procedures and ensuring that patient and staff are safe during exposures. So looking at international standards is the best options.
My X2 has a mass input. Does it mean it can measure mass?
Not by default. All units or all base units have the mass connector, but it is not always activated. So mass is included in many of our packages, but there are some where it's not. If the base unit has a caliber, oh, I can maybe show you. I have one here. If the base unit has a calibration sticker down here at the corner, it means that it has mass. If it doesn't hold any sticker, the mass port has not been activated.
Do filters age when X-ray machines are used?
No, maybe not by usage, but there might be some changes when it ages. X-rays are electromagnetic waves that doesn't really affect the matter it passes through, but the oxygen in the air may oxidize the filter, changing its characteristics. For regular radiography, the filters are usually that thick that a thin oxidizing layer doesn't really affect anything. But for certain mammography machine, the filters can be extremely thin and thereby gets more affected by oxidation. But manufacturers should be aware of this, and most of them have different ways of protecting the filters from this to happen, but there is always a risk.
Does the Xray tube age by not being used for many years?
Not the tube itself, since it's vacuum inside. There isn't really anything that could happen if there's no air inside. But the whole machine may, of course, age depending on how it's stored and everything.
So let's see now. We have quite many. So what is recommended calibration frequency of the sensors?
We do recommend to calibrate it every year, but it all comes down to you and your trust in the instrument, I should say, because during calibration, we of course do a checkup of the instrument, and when it leaves the calibration, we know that it is top notch. But as soon as the sensor leaves our calibration lab, we have no control of what's happening to it. So there is always a chance of the meter getting damaged or dropped or whatever throughout the years when it's handled. And when you send it for calibration and we say that it passes the as found calibration, it's the first thing that we do when we get a sensor in for calibration. It means that the sensor has been working well throughout the year. But if it fails the as found, it means that some time during the last calibration or between the last calibration, the meter was out of its specification. We had no idea when and where this happened. So it might be measurements that you have done with a faulty meter, one could say. I should still say that we have an extremely good yield when it comes to calibration. It is extremely few meters that fails as found, but there's always a risk. So it all comes down to how much you trust the instrument and your readings.
The survey sensors are directional and hence may not pick up scattered radiation in all directions. Are you planning to produce a non-directional chamber?
No, not that I know of. It is true that here it is. The survey sensor, for example, it will measure differently depending on how you angle it, and it prefers to have the radiation facing it straight. And most of the time you are aware of the source and you know how to position it and how to direct it. So from my understanding, it is not a big ask or a big issue for not taking up radiation for the full 360 or sphere around it. So no, there's no plan yet. But of course, if there's a big need, who knows what the future will hold.
I noticed when measuring dose from a CBCT rotation, in some situations, X2 starts measuring a few seconds later in clockwise when compared to anti-clockwise direction, and as a result, the total measured dose is a bit lower. I assume the reason is that there is a preset threshold for dose rate which triggers the measurement. Is this correct? If true, is there a way to change this threshold?
No, the threshold cannot be changed. It is true we have a threshold, but it's fairly low, and it shouldn't affect the dose that much. That's a very good question. I can't really give you a straight answer here and now why it differs depending on if it's clockwise or counterclockwise, because the geometry sounds like it should be the same. I would suggest that you send this question also to our technical support, where they, together with myself, could have a more deeper analysis of the case.
Is it correct that HVL measurements on CT scanners give relatively higher values, approximately 6 millimeter aluminium?
CT usually have higher filtration than other modalities, meaning that HVL will be higher in general, yes, but there are also differences between machines and brands and so on. But in general, I would say that HVL is higher on CT machine, yes.
Do the filters on your diodes get affected by radiation?
No, it's similar to the question I answered earlier, that the electromagnetic, the radiation is electromagnetic wave that doesn't really affect matter. So it doesn't affect the filters, but it can affect the electronics inside the sensor. But we have built in a lot of shielding around the electronics. So it will require an insane amount of dose for the sensor to actually get affected by the radiation. What can affect the filters is more likely if you drop it, mechanical shock or something like that.
What checks should be done if a sensor is dropped?
The easiest is, of course, if you have a second sensor and you do similar measurements and see if they behave the same. We have quite advanced self-test algorithms in our system. So when you insert the sensor, all this test runs before it's ready. And if there's something bad with the sensor, the system will tell you. But of course, there can be some minor cases where the self-test maybe don't pick this up. And well, either find a similar sensor and do similar measurements to compare, or in maybe worst case scenario, it might be a good idea to send it in for us to do calibration or check of it.
Are X2 sensors valid for beam quality measurements on CT scanners, given they have thinner beam widths?
Yeah, You can absolutely use the RF sensor, for example, for kV measurements on CT machines, just as long as the beam thickness or wider is wider than the gray slit here, which I showed earlier. So it shouldn't be any problem in measuring kV, HVL, and things like that using the RF sensor on a CT machine.
I think we have reached the end of the questions. So I hope that we have been able to answer all of your questions. And if not, you're always welcome to get in touch, and we will do our best to answer and give the information you need.
And you are always welcome to send more questions to technical support at RaySafe, of course.